So, hello everyone. Today we are going to learn about the thermal conductivity of a metal. So, till now we have been discussing about the electrical conductivity of a metal or a solid or a material. So now we are going to transition into the thermal conductivity of the material. Likewise, as we learned in Trudeau's model, we use the equation of motion to derive the electrical conductivity of a metal or a material. In this part also, we will be using the Trudeau's idea, some postulates to derive the thermal conductivity of a metal. So basically, this is a follow-up of Trudeau's theory, and you can say an application of Trudeau's model. All right. So for let me write down the heading. So thermal conductivity thermal conductivity of a material. So as you know that to have an electric current, you need to have a potential difference. At the two different ends of a sample, you need to have a potential difference for current to conduct within the material. Like that, you also need to have a temperature gradient to have a transfer of energy. Basically, what is this thermal conductivity? This is basically a transport of heat from one point of the material to the other. So basically a transport of energy, and this is heat energy. So let me just write down this, like electrical conductivity to be observed, you need to have a potential difference. All right. For thermal conductivity, you need to have a temperature gradient. Temperature gradient. All right. So highlight this. You need to have a temperature. All right. So thermal conductivity, you have to have a difference in temperature between the two ends of the sample. Okay. Let me just check if it's recording. Sure. Yeah. Sure. So fine. Now think of a sample. This is your sample, 3D sample. Whose one end is hot and the other end is cold. All right. So take a sample whose one end is hot, whose one end is hot. Note it by red. This is your hotter part. Fine. All right. Now this is the other end is a colder one. All right. So this is your folder. Fine. Now, what you're going to see is because of this temperature gradient, the hotter part and difference between the hotter part and the colder part, you're going to see a transfer of heat energy from one part of the material to the other part. Let's say from the hotter part to the colder part. So the hotter part is at temperature T1 and the colder part is at temperature T2. Naturally, T1 is greater than T2. Fine. You're going to see this transfer of heat energy across a cross section, right? Fine. So across this cross section, you're going to see the transfer of heat energy. The cross sectional area here is denoted by A. So this is your basic schematic where one part of the sample is hot and the other part is cold, and you have a temperature gradient. All right. Now you want to see the transfer of energy across this cross-sectional area. Cross-sectional area with area A. All right. So now denote the heat current density. You are going to see the measurable quantity that you are going to measure is the heat energy per unit area per unit time. That is the heat flux. As you know, for intensity, you know energy per unit area per unit time. All right. So now in this case also, you're going to see the transfer of energy across a cross section per unit area per unit time. So let that be denoted by J of Q. This is your heat current density or heat flux. As you know, flux is energy per unit area per unit time. So now you can understand it will be divided by cross-sectional area and rate of change of heat. All right. So this is the quantity that you are going to measure. So JQ, which is the heat current density, let me tell you, JQ is dependent on the temperature gradient across the sample. This is simple because for transfer of energy, you need to have a temperature difference. This transfer of energy is only because of the difference in temperature that the sample possesses at its two ends. So it is natural to think that the heat energy transferred will be dependent on the temperature gradient. Not only that, in addition to that, let me redraw the sample. In addition to that, if this is your sample, sorry, drawing it's messed up sometimes. So if this is your sample, this is your sample. Okay. So one end is hot, and the other end is cool. So, and this is the length of the sample. Fine. This is the length of the sample. Now, this is a temperature T1 and this is a temperature T2. So, if there exists a gradient of temperature across the sample, in addition to that, how much is the difference? If, let's say, if you draw a graph of this T1, T2, this T1 and T2, this is the graph. This is the variation of temperature across the sample. So this is your T1 and this is your T2. If this gradient is large, so the heat flux will also be large. So compared to this, if the graph is like that, if the temperature gradient is like that, such that the difference between T1 and T2 is not that great, not that great of a difference, the heat flux will be lesser. So your JQ is proportional to the temperature gradient across the sample. More is the difference in temperature, say between point A and point B, between the two ends, more will be the heat flux transfer. So heat current not only depends on the temperature difference, but also on the gradient. This means that what distance this difference is maintained. So what I'm trying to say is that it not only depends on the difference T1 minus T2, but it also depends on the gradient, the distance over which this difference is maintained. That is dt over dx. All right. So we were considering in one direction only. So for all the three directions, this JQ will be proportional to dt over dx. Except likewise, this JQ is also proportional to dt over dx y cap. Similar for the z cap reaction. Fine. So combining this in all the three directions, this can be written as JQ is equals to some proportionality constant kappa dt over dx, just addition of all the components. All right, dt over dy y cap plus dt over dz z cap, fine, which is given by minus of kappa gradient of T, so temperature. This kappa is called the thermal conductivity of the material. All right. So the proportionality constant is the thermal conductivity of the material. So now, normally you can think that this negative sign is for convention only. Like you draw this graph. Let's say this is your temperature T1 and this is your temperature T2. Fine. So this is your delta X. All right. So the quantity dt dx will be given by the difference in temperature. Let's say, let me write this informally. T is dU over delta X. So as because T1 is greater than T2, this quantity is negative. So the natural thing that follows is that you need to adopt a negative sign in front of it. Negative sign to take care of this negative gradient. Fine. This is for conventional purposes only. So our basic picture is that you have temperature T1, you have temperature T2. This is your water portion, and this is your cold portion, and there's heat flow in between this. This is the basic framework that we are working in. So with this in mind, we want to proceed in calculating the thermal conductivity of the material. Redrawing it again. So this is your sample. Okay. So this is your hotter part. This is the colder part. This is hot. This is your hot part. And this is your fine. And let's do this for a 1D sample. And now, and after that, we will proceed to do the 3D case. All right. So you want to look the transfer of energy across this point X. So this is your 0 point. So you want to see the transfer of energy across this point H. Net thermal current across the point X is what we are going to see. Fine. So now, which are the ambassadors of this heat flow? The charge carriers. The only option is that you have electrons. Electrons, the charge carriers, they also conduct this transfer of energy from the hotter part to the colder part of the sample. So electrons are the charge carriers. Electrons are the charge carriers that transport or conduct energy and the momentum. Electrons are the only candidates. All right. They help in electrical conductivity, but also they are the charge carriers which help in the conduction of the thermal current. All right. One basic assumption of this framework that we're working in is that we need to assume we need to assume that electrons are coming from both the hot end and the cold end. No, still now we have eight. Okay. So you have to assume that electrons are coming from both this end. Electrons are coming from both this end and also this end. Fine. So without some numbers, then with the density of electrons, inside the metal. So for equidistribution, let then n by 2 be the number density, of course, be the number density of electrons crossing X from the hotter end to the colder end. Also, n by 2 is the number density of electrons crossing X from the colder to the hotter end. Fine. All right. So, as because electrons are traversing, retrying again. So, this is your sample. This is your X. This is your hot part. This is your cold part. And n by 2 electrons are coming from this end hot end. Also, n by 2 electrons are coming from the cold end to the hot end. So, at a point X, as equal number of electrons are coming from the hot end to the cold end and cold end to the hot end, there's no charge addition at any point. Only they act as carriers of thermal energy. Only transfer of thermal energy. Fine. So, for the final time, we're going to derive it from now. So, this is your sum. So, this is your hot end. This is your cold end. This is the point X across which you want to see the transfer of energy. This is your point X, and n by 2 electrons are coming from this side. Equal number of electrons are coming from this side, the port side. All right. So now, recalling the second postulate, that in between two collisions, the electron, second postulate of the Trude's model, that in between the two successive collisions, the electrons, this, of course, this is a postulate of kinetic theory also, kinetic theory of gases, that in between two successive collisions, the electrons will move in a straight line, and the mean time scale between two collisions is tau. The implication is that in between this, within this time scale tau, there will be no collision. So, if you consider at an earlier time t minus tau, so this is t, so an earlier time tau, t minus tau, of course. So, the mean free path is given by the path is given by v times tau. V is the mean average velocity between collisions. So, at a later distance for an electron, at a point that is x minus v tau, that is at x minus v tau. This is x minus v tau. This is x. So, let's draw at point further away from the point x. This is x plus v. Slowly we will get into this. So, consider an electron at a point that is at v tau distance behind the point x. What are the implications? Is that the electron at this point will stay unperturbed and move in a undisturbed fashion with a constant velocity, because the assumption is that within this time scale tau, the electron will not undergo a collision, and the distance traversed by it will be given by the mean free path, which is the product of v times tau. So it will go undisturbed from the hotter end to the colder end. Fine. Likewise, at a distance v tau ahead of the point x, the electron, which is coming from the colder end, will also travel in an undisturbed fashion. Fine. It will be left undisturbed because it is in its mean free path and no collision will occur in its path. So it will carry momentum from x minus v tau to x. Likewise, from the colder part also, electrons from x plus v tau will transfer momentum to x. So the energy of the electrons will be a function of temperature. So this is your T1 and this is your T2. So energy of the electrons on the hot end side, will be given by x plus x minus v tau. So there exists a temperature gradient across the sample, as I said earlier, which is the main cause for this transfer of heat energy or heat flux or heat current. All right. So this energy at a point, let's say at x minus v tau, will be dependent on the temperature at that point. So naturally, the energy of the electrons on the hot end side, let's say at this point, at this point, at this point, will be given by epsilon, which is a function of t, and t at point x minus v tau. Similarly, energy of the electrons on the cold end side will be given by epsilon t of x plus v tau. We assume that electrons are going to come from both the hotter end and the colder end, and you are going to see this transfer of energy through these electrons at a point x at a cross-sectional area. Fine. So this is what we are at. Now calculate the net heat flux. Ultimately, we have to calculate the heat flux. So point number one, net heat flux from the hot end to the cold end. It's simple to write because this heat flux will be energy per unit area or unit time. So this will be given by the number density of the electrons times the mean average velocity times the energy. Fine. So this is number density. This is divided by volume. If you see dimension, this is divided by volume times a velocity, which is per unit area per unit time. Fine. Times the energy. So the energy flux is given by this formula. So dimensionally, it is also consistent. Similarly, net heat flux from the colder end to the hotter end is given by similarly n by 2, but in this case the electrons are traversing in the negative x direction. Fine. So the mean average velocity will be given by minus of v. This is epsilon v of x plus v of tau. Fine. Now, if that rings a bell in your mind, so we can Taylor expand this. So t, which is a function of x minus v tau, is also a function of on the hotter end it is function of t of x minus v tau. On the colder end it is t of x plus v tau. So before that, so the net heat flux across the point x, so the net heat flux across the point x will be given by 1 plus 2. So the net heat flux from the hot to the cold end plus the net heat flux from the cold to the hotter end. So let us first Taylor expand this. Taylor expanding T of x minus v tau will be given by T of x minus v tau times dt dx, and here we are ignoring the higher order terms. All right. Similarly, T of x plus v tau will also be given by T of x plus v tau dt dx, and also ignoring the higher order terms. Fine. So let us denote it by x minus v tau as t minus del t. It's omitting the x dependence here because it's there, but I'm not writing it. And also, t of x plus v tau will be given by t plus del t. This is the extra temperature. All right. So now the net heat flux is equals to n by 2, which is times v times epsilon t minus uh, epsilon of t minus del t minus of epsilon t plus del t. If you notice closely, this is again a Taylor expansion. And this will be given by n by 2. And we are going to ignore the higher order terms, only taking the first derivative. So this is n by 2 times v times epsilon at temperature T minus del T times d epsilon dt. Fine. Minus of epsilon tau T plus del T d epsilon dt. You can easily see that the first terms, the containing epsilon t and epsilon t on the other side, this will cancel between themselves. So these terms will cancel out, leaving us with minus n v times delta t times and this is your d epsilon times dt. Putting the above terms into this, minus n v times v tau times d t dx times d epsilon dt. Fine. All right. So this is minus n v squared tau times dt dx times d epsilon dt. Sorry, this is too late. I have to write this first. So you'll see why I'm trying to write it firstly. So epsilon dt times dt dx. As we said, and also wrote the formula that your JQ, which is the heat current, is 1 over A dt dq dt, sorry, q dt, which is also given by minus kappa times dt dx. The heat flow not only depends on the temperature difference, but also on the gradient of the temperature, the distance over which this difference in temperature is maintained. So this is your familiar form of kappa, which is given by kappa is equals to n v squared tau d epsilon dt. So this is your final form of your kappa, or the thermal conductivity. Understood? So kappa is n v squared tau times d epsilon dt. Remember that d epsilon dt is your specific heat, the rate of change of temperature with a given supply of energy. So Cv specific heat is your dE dt. So kappa can also be written as kappa is equals to nv squared tau Cv. All right. Now we worked out the problem in one dimension. Similarly, Kx is in the x direction. What is the transfer of energy? And this is independent. This is independent of the direction. All right. So in the x direction, this will be given by nvx squared tau d e dt epsilon. I'll be changing from de or d epsilon. So please bear with me. So kx will be given by nvx squared tau times d epsilon dt. Ky, sorry, this is kappa. This is not k. So this is kappa. Is equals to, this can be confusing with the wave vector. This is kappa. And this is also equal to nvy squared tau d epsilon dt. Similarly, kappa z will be given by nvz squared tau d epsilon dt. Now, for an isotropic sample, there's no reason to believe that what's happening in the x direction should be very much different from that in y or z direction. So combining this, your from kinetic theory also we derived that the mean average velocity in x direction is roughly equal to 1/3 of the total velocity. Okay, square of the velocity, of course. Let me just correct myself. So this is 1/3 of the total mean average squared velocity. All right. So why this is happening? Because this is an isotropic sample. We have not included an isotropy in the sample. So in x direction, what's happening? It's not very much different from what's happening in the y or the z direction. All right. So now our kappa can be further modified to be written as kappa is 1/3 n v squared n v squared tau times c. All right. So if you recall from kinetic theory that the mean squared velocity, the mean squared velocity from kinetic theory is given by, I'm writing the exact form, 8 kVt over pi times m. All right, m is the mass of the particle in the sample. All right. So now still kappa can be modified to be written as 1/3 n times 8 kVt over pi m times tau times Cv. From kinetic theory, we already derived that the specific heat is given by of course per electron. The specific heat per electron is given by 3/2 kV. For n electrons, it's given by 3/2 n kV, which can be further written as 3/2 R. So per electron, the specific heat will be given by 3/2 kV. So manipulating this, simplifying, we get 4 over pi times n tau times kV squared into E times m. All right. So the kappa is given by 4 over pi times n tau kV squared T over m. So is there any connection between the thermal conductivity that we calculated, and in the earlier lectures we have been calculating the electrical conductivity. So electrons are both charge carriers. They conduct electricity from one point to the other. Conventionally, the direction of current is opposite to the movement of the electrons. Now, electrons are the only agent that transfer the energy, the thermal energy, from a hotter end to a colder end, along with carrying a charge. All right. So, is there any relation between this thermal conductivity and electrical conductivity in question? So, we're calculating for the umpteenth time your sigma electron electrical conductivity denoting is given by n e squared tau over m. Now, if we define a ratio which is given by kappa by sigma times the temperature of the sample, this will be given by 4 over pi times n tau times kb squared t over m divided by n e squared tau over m. So the terms, so this is also t in it because we have divided t. So the terms that cancel, this is p cancels, this n cancels, this tau cancels, and also this m cancels. Finally, what we are left with is 4 by pi. So this is weird to write in different colors in the same single derivation. So this is given by 4 over pi kb squared over e squared. What is this? So the ratio of the cap thermal conductivity and the uh, electrical conductivity times the temperature is a constant. This is a very important name and law. It falls in a very important law which is given by the ratio is given by L, and this is prediction of the Wiedemann-Franz law. This is your Wiedemann-Franz law, which says that the thermal conductivity is proportional to the electrical conductivity. So by this, you can write that kappa is equal to L times T times sigma. Therefore, kappa is proportional to the thermal, electrical conductivity, and the constant, the proportionality constant Lt is also constant. All right. So, which is redundant to say, of course, this proportionality constant, this L, the ratio is a constant, I should rather say. So, what does this imply? That the sample or a material and the electrons in it with higher electrical conductivity will also have higher thermal conductivity. All right. So, electrons in a material with higher electrical conductivity will also be a very good thermal conductor. All right. So I have to produce some numbers that some this constant L, so it's a ratio of thermal conductivity to the your electrical conductivity. You have to produce some numbers. Let's say for copper, for silver, for gold, and for aluminum. This is L and it has units of watt ohm per Kelvin square. So for copper, it is 2.29 times 10 raised to minus 8. Sorry. For silver, it is 2.38 times 10 raised to minus and 2.36 times 10 raised to 8. 2.19 times 10 raised to minus. The theoretical predictions were given as theoretical value. This is 2.22 times 10 raised to minus 8 watt ohms per Kelvin square. So it is more or less the same as to the theoretical value. All right. But at hindsight, if you look at it, so this is your this your L, so kappa. So let's just stop here. So we will be proceeding in the next class. So today we learned about the thermal conductivity of a material and how and whether or not it has a connection with the electrical conductivity. We answered it with that the ratio remains constant and it's the very popular Wiedemann-Franz law. So we read about the thermal conductivity. We derived that for a thermal conductivity to happen, it needs to have a temperature difference. And not only temperature difference, it has to have a temperature gradient across the sample. Means the temperature difference to which distance it's carried through. All right. And we wrote down a formula for the thermal conductivity, which is given by 1/3 n mean average per velocity times tau times the specificity. It also has some alternative forms which we wrote. So we just stop here and